Hi! One of the most important applications of differential calculus is its use in solving optimization problems. We could say that much of our daily life involves solving such problems. Consider, for example, questions like which route should I take to arrive faster? Or how should I optimize on energy consumption at home to save on the electricity bill? Or again, how should a company optimize production to maximize profit? In general, real-world problems are very complex, especially due to the number of factors on which the system depends. So how can problems formulated in this way be solved? In this video, we aim to understand how to solve them by using the tools provided by differential calculus. The resolution process involves three stages. First, the problem setup. This stage transitions from a descriptive formulation of the problem to its mathematical formulation. It involves identifying three key elements. First, the variables of the problem. These are quantities that are free to vary within a certain domain and are the variables for which we seek the optimal configuration or configurations. Second, the parameters. These are quantities that enter in the problem and influence the system but remain fixed, unlike the variables. They are useful because they often express conditions and constraints among the variables. And finally, the target function. This is the quantity to be maximized or minimized as a function of the problem variables. So once the problem is properly defined, it takes the form of determining the maximum or the minimum of a numerical function of a certain domain. If this function is a function of one real variable, we may use the tool of differential calculus. So, for instance, we compute the derivative of the function, we discuss whether the derivative is positive or negative to determine where it is increasing or decreasing, and then we identify the extreme points, which are the solutions to the problem. At the end of this step, there are the conclusions. That is, we have to give an interpretation to the results obtained from the solution of the problem. Great. Let's explore this process with a particularly simple example. Here, the goal is to illustrate the method rather than solving a difficult problem. We begin with the classic geometric problem, namely the isoperimetric problem. This is a problem with a very ancient origins. In fact, the legend says that Dido, the queen of Carthage, exiled by her brother, requested a piece of land equal to the area she could enclose with a strip made from an ox hide. On this area, Carthage would have been founded later. Now, the point is, what area should Dido have enclosed to obtain the largest possible plot? This involves solving the problem of finding the maximum area of a shape with a fixed perimeter, which is named the isoperimetric problem. Now, this problem in the general form has been solved by Bernoulli only in 1696, so about 1,000 years later when the problem was posed. But here we see a baby version for this problem, namely the following. What is the largest rectangle that can be enclosed with a fixed length rope? Now, if we formalize this problem, we can represent rectangles knowing the sides x and y. Different rectangles will have different sides. So we may consider that x and y here are positive because they are lengths of sides are the variables of this problem. Now, the area of the rectangle is just the product of the two, while the perimeter is the double of the sum of the two. In this problem, the perimeter is fixed, so it plays the role of a parameter, while the area is the target function. It is the quantity we want to maximize. So the problem consists in solving this. Find the maximum of x times y on all xy positive, and such that x plus y is equal to p divided 2. Now, under this form, it is a problem for a function of several variables. But thanks to this constraint, we can also write that y is equal to p half minus x. So we can reduce the number of variables here, transforming this into the problem for the maximum of x times p half minus x when x is positive, and moreover, since also y must be positive, x cannot be just any positive number, because this quantity must be positive, and this means that x must be less than p half. So now here we have a function of one real variable that has to be maximized on this interval. So it is at this stage that we can use the differential calculus to solve this problem. So we can compute the derivative of f, which is equal to p half x, so the derivative is p half, minus x squared, the derivative is 2x. So this is greater or equal than 0 if and only if 2x is less than p half, so x less than or equal than p over 4. So we see that on the interval from 0 to p half, we have p over 4, which is the midpoint of the interval. The derivative is positive from 0 to p over 4, and it is negative from p over 4 to p over 2. And moreover, this function is clearly well defined and continuous here. This means that that point, p over 4, is the maximum for the function f. And therefore, this is the optimal x equal to p over 4. Now we go back to the initial problem, since there is also an optimal y, which corresponds to x through this condition. So we get the optimal y is p over 2 minus p over 4, so p over 4 as well. So now we have the interpretation of the result. So we conclude that the optimal rectangle with maximum area fixed perimeter is a square of side p divided by 4. A dual problem is the isovolumetric problem, that is, among all the rectangles with fixed area now, determine that one with the minimum perimeter. So we can formalize similarly. So we use still the sides of the rectangles of variables. We have that the perimeter is 2 times x plus y, which is now the target function. And the constraint is provided by area, which is constantly equal to a, say, fixed. So we have to solve for the maximum of 2 times x plus y, known that x and y are both positive, and such that their product, x times y, is equal to a. Again, we can reduce this problem to a one-variable problem, because we can use the constraint. Knowing that the variables are positive, we can write, for example, y equal a over x, and this becomes the maximum for the x positive of 2x plus y is a over x. And there is no other condition about x, only x positive. So now we have to consider this function. We can choose just a factor, and we apply differential calculus to this function. So we start computing the derivative of this, which is equal to the derivative of x is 1, and the derivative of a over x is minus a divided x squared. So this is greater or equal than 0 if and only if a over x squared is less or equal than 1, or x squared is larger than a. And since here x is positive in the problem, this means that x must be greater or equal than the root of a. So it means that we have this diagram from 0 to plus infinity. There is value root of a, where something happens. Then the derivative is positive for x larger than root of a. So this means that on the interval root of a to plus infinity, the function is increasing, while on interval 0 to root of a, the function is decreasing. At root of a, the function is well-defined and continuous, so it means that this is a minimum point for the function f on 0 plus infinity. So this shows that the optimal x is equal to root of a. And from this, we get also the optimal y, precisely from this formula. A divided root of a gives root of a. So we conclude that the optimal rectangle that has minimum perimeter with fixed area A is again a square of side root of A. Good. I hope this gives you some useful ideas on how to tackle problems like this. The best thing you can do now is, of course, to try solving some problems yourself. Here are two suggestions. One is simple and similar to the ones we have seen in this video, and the other is more challenging. Well, good luck!